This is the final demo for Group 16, Fall 2024. For our engineering specifications, we had three major components that we wanted to successfully satisfy, starting with the dish with a gain of 9 dB. For the Raspberry Pi, we wanted the complete mapping from when we start data collection to the heat map being plotted to be less than 5 minutes. And for the stepper motor drivers, we wanted the setting speed to be 4.5 degrees per second.
So this is the radio telescope that we designed. As you can see, it is fully 3D printed with a camera gimbal that we repurposed to hold the radio telescope on top of. As you can see here, it has a base with a threaded hole that holds the counterweight on the bottom. Back here is the fan that cools the system, and up here we have a e-stop, an emergency switch. Now, what you see here is the base, which holds the rest of the radio telescope. Inside we have the electronics box, and on top of that we have this segmented parabolic dish, which has a focal point at exactly 13 centimeters, which was calculated. And in the gimbal design, we have two stepper motors, one that controls the tilt and one, as you can see, that controls the x-axis, allowing it to rotate a full 360 degrees. So inside the electronics box, we have the entire electrical schematic. We have the battery, which goes through the switch, which goes into the main PCB. The main PCB powers, the regulators power the main PCB, which powers the stepper motor drivers, and this communicates with the Pi. The Pi is powered by an external power supply that we'll have outside of the box. And other than that, the Pi will also power the SDR, which is the software-defined radio, which will be receiving the signals. And other than that, we have two more cables that plug into the LCD screen that we will be using to control the motors as well as display the heat map.
Alright, so to power this, we have a 12-volt battery. This is our on-off switch. That then goes into a regulator that boosts it up to 15 and then back down to 12. This is to power our motors. And then over here, these regulators go and bring the 12 volts down to 5 and then down to 3.3 from there, and that is to power our ESP32. And then on our main board, our ESP32 is what will tell these motor controllers to spin the motors. And then we also have a CP2102 chip for a USB to UART bridge so that this can talk to our Raspberry Pi. The Raspberry Pi uses our software to produce the heat map from our readings from the antenna.
So now I'm going to show you how the tracking works with our radio telescope. First, I'm going to initialize the system for setting the initial points. Once I do that, it should say that it is ready. And then, for example, we're going to put about 10 degrees for X and then 15 degrees Y for the initial point. And once I hit apply, you should see the motors move to the specified. So at this point, it should move to 15 degrees. And when it rotates this way, it should move about 10 degrees. As you can tell, it also confirms that it's been set. For the endpoints, we also need to initialize that to let the ESP32 know that it's about to receive those points. And for X, I'm just going to move it by 10 degrees. For both, I'm going to move this to about 30. We're going to double that as well. And then I'm going to set it. At this point, it should be able to recognize that. And then for the time duration, we're going to do the same thing. Initialize the system, letting the ESP32 know it's going to receive time. And we're going to put it for about 100 seconds. So once we set that, we should be able to essentially start tracking. And the tracking interval kind of calculates every, as you can tell, it moved. And over time, it should be moving the system as well. while we're waiting for that, you're gonna see it move one more time. You're gonna see, yeah, you see it moves. So it calculated the difference to do that. So now I'm gonna stop the track. That's not the only way to stop the tracking. It's also once 100 seconds have passed, that's another way. And now I'm gonna reset the motors. And then right now when we reset the motors, it's gonna go back to the initial position where it was earlier in the video.
I do see some things that we're making changes next month.
And right now it's at 0, where it was the initial position. Also within this, you can also do plotting and the heat maps, and that's a separate process, but it's all into one GUI. Right now we're going to do trial 1 of the motor's rotation per minute. We're going to do essentially, we're going to calculate the degrees per second, so we're going to essentially input the degrees in the set feature, and then we're going to take the time total elapsed, and then we're going to essentially divide that and figure out the degrees per second. So now we're going to do the first trial, which is 30 degrees X and 20 degrees Y. And once it hits enter, it should move. And as you can see right here, the total time elapsed for the Y degrees is 6.6 seconds, and for X it would be 7.92 seconds. For trial 2, we're going to go with a little bit more load on the radio telescope. We're going to do 123 degrees X and 40 degrees Y. And let's do that right now.
That's not good news. You see how hard your work's gonna be? Right? Yeah.
And as you can see, it's moving 40 degrees, and then once it hits 40, it's going to move 123 degrees, which is a large amount. You do have to be wary of this cable.
Make your first prototype this big. When it works, then make it this big. You know what? I'll make a deal.
It should be towards the end of this. It should be right about now. And then right now you'll see for the Y, it's about 13.26 seconds, and for the X, it's 32.7 seconds. For trial 3, we're going to do 25 degrees X and 35 degrees Y. I'm going to press enter, and you'll see it's going to move.
You say you're into stuff personally?
So right now it's moving the Y first, and then after it sets the Y, it's going to set the
I
X.
use 183. They also make 138. Use 138 when
And now it's moving about 25 degrees X right now. Once that's done, right here we'll see for total elapsed time of Y is 11.53, and the total elapsed time for X is 6.6. After we completed 10 trials, we were able to see that the degrees per second managed to stay within our 4.5 degrees per second threshold. Things I do want to know is whenever we have an X position like 107 and negative 107, that the X time is the same, and that is as expected because it is a symmetrical position. And another thing we want to highlight is the X position and Y position where they're both 47, and the reasoning behind that is because the X gears have a smaller ratio than the Y gears. The X gears have about an 8 gear ratio between the smaller gear and the larger gear, and the Y has about a 10 ratio between the smaller gear and the Y gear as well.
Go.
Alright, trial 1 of testing how long it takes for data to be collected on computing radio to actually plot in the heat map. So we're going to plug in the signal that we want, which is 1.425 gigahertz. Alright, plug in a sample rate, and we're going to set the motors to 10 and 10. Apply. So it's gonna move. We're generating a signal in the lab here. Alright. And we're gonna go ahead and just start the data collection, and I'm gonna hit the timer on my map at the same exact time. Alright. So it's collecting some data on that signal right now. And we're gonna go ahead and see here, that is a signal that we're reading in. Wait about 5 or so seconds. So it's collecting some data. Close it. Let's plot this heat map and see how strong that signal is. Right, so you can see it's coming in pretty strong right here. Has a little bit of noise, so it's picking up some others, but the intensity value of dB40 is what we're getting. And that's taken approximately, let me close this, about 40 seconds. Trial 2, we're listening to signal 918 megahertz, same sample rate, that's the best one right now for Raspberry Pi. We're going to move the angles at 5 and 5, so I'm going to hit apply. We'll watch it move. Alright. And I'm going to go ahead and start the data collection at the same time. Right. And you'll see GNU Radio pop up, and it should be reading at 918 megahertz, which you can see our signal there. We'll go ahead and close, and we'll plot. Again, you can see a little bit of noise here, but the strongest signals are mapped in yellow and they're super bright. And the intensity of the dB gain is here where you can kind of track and see that. We'll close this, and that took about 35 seconds. Trial 3, and we're going to move the frequency to 989 megahertz. Sample rate, we're keeping it the same. We're going to go ahead and initialize the system, setting the X and Y to 8 each. We'll hit apply, watch it move. Move just a little bit. We're going to hit at the same time. So it's going to collect a little bit of data. There is our signal. It's coming in pretty strong right about there. And we're going to go ahead and exit out and plot what we just saw there, but heat map version. And like before, we can see the signal's really strong right here, not as much noise. And we're going to go ahead and close the program and stop 32 seconds. For the radio mapping time, so we pretty much picked a frequency channel to tune into, and the goal was to map this less than 5 minutes. You can see in the furthest right table the actual time. It was a roughly averaged around, I would say, 35 to 40 seconds, depending on how long we let the data collection run for.
All right. For trial 1, we're gonna move our dish to we're gonna keep the X the same, but we're moving the Y down to 15. Currently it's at 10, so if you want to hit 15 and see it move down a little bit, as you can tell, 15, and then the spectrum analyzer right here is reading about negative 79 dB. This is trial 2. Right now we're going to put the dish at 30. Previously it was at 25, and after that we're going to read what the spectrum analyzer has to say. While we move it using the Raspberry Pi program, we're able to see it is about negative 76.5 dB. This is the trial 3. We're going to put the dish at 45 degrees. Once in the Raspberry Pi program, as that it's at 45 degrees. This is right now at about negative 72 dB.
Trial 1 with our dish, and we're going to 15 degree. And it's reading negative 74.1 dB. And now negative 73. Trial 2 going to 30 degrees. And it's reading negative 69.6 dB. Now it's up to negative 70.1. All right, we're testing at 45 degrees, trial 3. And our gain is negative 66 dB.
As you can see here in the radio dish for the y-axis gain, at 25 degrees we see a 9 dB gain with the dish versus without the dish. So from the wide axis trials, we were able to determine that our dish gives about 9 dB worth of gain. And here's the results from our x-axis tests. As you can see here, with and without the dish, we do see some gains and some drops depending on the angle of the dish. It all depends on if the dish is blocking the signal from the signal generator or the way the dipole is mounted.